Good day, doctor. This is the video presentation for the KIE3009 assignment. I am Lee John and my group members are Chong Wei Jie and Ying Chi Wen. Okay, hello everyone. I'm Lee John and I will be presenting the solution for Task 1 bus admittance matrix. So here's the equivalent circuit for the three-phase power system consisting of 7 buses, and I have labeled all the reactants for the lines and the reactants for the generator here. And then the first step will be finding the bus admittance matrix. So because it's a power system consisting of 7 buses, the matrix will be a 7 times 7 matrix, which you can see from here. It will be the elements inside will be Y11 all the way until Y77. And then for each of the elements inside, as for Yij, when I is not equal to j, which will be the Y12, Y13, Y14, Y21, Y23, and then the values will be the line admittance of that particular line. And then as for I equals to j, which is Y11, Y22 all the way until Y77, it will be the admittance that is connected to that bus. So this slide is showing all the calculations for the elements in the Y matrix. And as you can see here, for Y11, it will be the sum of all the admittance connected to that bus. As for the yi not equal to j, it will be just the line admittance. And then as for the line that is not existing, for example, the Y13, there's no line that exists between bus 1 and bus 3, it will be just 0. Okay, so after calculating all the values inside the Y matrix, this will be the final result for the bus admittance matrix Y. And then to obtain the bus impedance matrix Z from Y, I use MATLAB to inverse the Y matrix. And then the result is shown here for the Z matrix. So this is the MATLAB code implementation for obtaining the bus impedance matrix Z from the bus admittance matrix Y. So after obtaining the bus impedance matrix Z from Y, the next step will be calculating the fault current. By assuming the pre-fault voltage at all buses will be 1 per unit, and also the fault impedance is 0 per unit. The fault current at bus 7 is calculated using the formula, and the result obtained is negative 18.76 J per unit. So after obtaining the fault current, then we proceed on calculating the voltage at every bus after the fault occurs. So the voltage at every bus will be Vi fault is equal to Vi initial, which is Vi0, minus the impedance, the line impedance, times the fault current. So the voltage for every buses is calculated here from V1F until V7F, as you can see from the result here. So after obtaining the voltage at every bus, we can now calculate the current in every line. The current in every line is calculated using the formula Ij fault equals to Vi fault minus Vj fault, all divided by the impedance of that line, Zij. So for example here, I12 fault is equal to V1 fault minus V2 fault divided by Z12. And every line, the current is calculated here. And for the line that doesn't exist, for example, between bus 1 and bus 3, there's no line connecting the bus 1 and bus 3, so the current in that line will just equal to 0, which is not calculated here.
Moving on to the simulation using Powerworld, we first need to set up the circuit as shown here. Each bus must have a nominal voltage of 13.8 kV. The load for bus 3, 4, 5, and 6 are set to 100 MW. The load for Both generators have a maximum range of real power and reactive power to be 10,000 mega, while the set point for real power is set to 100 megawatt. Bus 1 is set as the slack bus or reference bus. This is shown with a slack word shown at the generator attached to bus 1. The internal sequence impedance for both generators are set to 0.00001 in the fault parameter section. The reactance X for both generators has to be set according to the assignment question: 0.045 per unit for generator 1 and 0.055 per unit for generator 2. Each line connecting between the buses have each own series reactance in the per unit impedance parameter section, as specified in the assignment question. Besides, we need to ensure that the nominal voltage of each line is 13.8 kV and the limit A in the MVA limits section is set to 1000. To observe the current flow, go to the Run mode and then go to the Tools tab. Then run the fast decoupled power flow under the Soft drop-down menu. The result is shown as displayed. To simulate a bolted symmetrical three-phase fault occurring at bus 7, we need to first set all the loads and generators to 0 megawatt. Then, we go over to the Run mode and click on the fault analysis section. A tab will pop up, and we need to go to the single fault at the left-hand side. Set the fault location as bus fault, and the fault type is three-phase balance. Choose bus 7 as the faulted bus. The fault impedance for a bolted symmetrical three-phase fault are both zeros. Finally, click the Calculate button. To observe the bus voltages, we navigate to the Bus Records tab. The three-phase volt A, B, and C are the same since it is three-phase balance. It was observed that the values for the bus voltages are almost identical to the theoretical bus voltages obtained in Task 1 via bus admittance matrix method. On the other hand, we can navigate to the Lines tab to obtain the line-to-line current. The phase current A, B, and C will also be identical due to the same reason. The values observed for the line-to-line currents is also similar to the calculated values, thus validating each other.
We'll begin with task 3.1, a comparison between our manual calculations from task 1 and the software simulations from task 2. First, looking at the total fault current, we can see an excellent argument with both the calculated and simulated values at 18.7 pu, resulting in a near 0% difference. The table below shows the post-fault voltage at each buses. Here again, the results are very consistent with all differences well below 1%, validating the accuracy of our models. Continuing the comparison, this slide shows the line currents during the fault. While there are some minor differences, generally under 2%, the simulated magnitudes align very well with our calculated complex values. This strong correlation across all metrics confirmed that our manual analysis in task 1 was successfully validated by the Powerwall simulation. Next, in task 3.2, we analyze how fault locations affect current magnitude. The data clearly shows an inverse relationship. As a fault moves further from the source bus, the current decreases significantly. The theoretical reason is that a longer line path adds more impedance to the circuit. As the formula I equals V over Z shows, higher impedance leads to lower current. The key practical implication here is for protection engineering, as relays must be set to detect both the high near-in fault currents and the much lower remote fault currents. Moving to task 3.3, we explore two methods to reduce fault current. The first method is to increase the line reactance connecting to the faulted bus. The concept is to add series reactors or use higher impedance lines to intentionally increase the system's Thevenin impedance. Our simulations prove this is highly effective. By progressively increasing the reactance of the three lines feeding bus 7, we successfully reduced the fault current from over 18 per unit all the way down to 3.6 per unit. However, this engineered solution has significant trade-offs. The societal pro is enhanced safety and equipment protection, but the con is degraded power quality and reduced grid stability. Environmentally, this method requires a larger land footprint, consumes more resources, and introduces continuous energy losses, which increases the system's carbon footprint. The second method analyzes the effect of fault impedance. This isn't an engineered solution, but rather models a realistic, non-ideal fault. Here, the fault itself has an impedance, which gets added to the total. Our simulation shows that by introducing just zero point 0.1 per unit of fault impedance, the fault current was massively reduced from 18.7 down to 6.5 per unit. Despite reducing the current, high impedance faults present a major societal risk. They are difficult for protection systems to detect, posing a severe electrocution and wildfire hazards. Environmentally, these faults are often caused by interactions with nature, like trees or animals, and their most dangerous effect is the potential to ignite catastrophic wildfires.
Thank you for listening. Thank you, doctor. Thank you.